Hello everyone, in this video I will be discussing various electrical engineering concepts and principles, and I will be focusing on diodes, CCD and CMOS, photocells, solar cells, and transistors. At the most basic level, the diode is an electronic device that allows current to flow in one direction. An I-diode diode would offer zero resistance in one direction while having infinite resistance in the other. Of course, this isn't realistically possible, so practically most diodes have about 1,000 to 10 million ohms of resistance instead of infinity. To understand how diodes work, we must first go over semiconductor doping. Most semiconductors are made of silicon, which is what is depicted here. A silicon atom normally has 4 electrons in its valence shell. Pure silicon is very stable as a result and forms covalent bonds with other silicon atoms. When an n-type dopant, such as phosphorus, is added, the semiconductor is given an extra electron that can freely move, which creates an n-type semiconductor. Similarly, when a p-type dopant, such as boron, is added, the semiconductor receives a hole, creating a p-type semiconductor. It is important to note that when a semiconductor is doped, it is not charged despite having free electrons and holes. The dopants are neutral atoms added to neutral pure silicon, which forms a neutral semiconductor as a result. Diodes are created by doping p-type and n-type semiconductors and connecting them together, creating what is called a p-n junction. The p region has excess holes and the n region has excess electrons that can all freely move. When connected, the holes attract the electrons and diffuse, which forms a depletion region. This depletion region is what gives diodes special properties when current is applied to it. First, we will go over what is known as zero bias, which is when there is no external current applied to the diode. In this case, the diode is in equilibrium and has negligible voltage. Sometimes there are very small amounts of voltage and current that are a result of electromagnetic waves knocking electrons off. When the diode is connected such that the positive terminal leads into the p region and the negative terminal leads into the n region, excess holes and electrons form on the other side, which applies pressure onto the depletion region. This is what is known as forward bias. This decreases the size of the depletion region, and its resistance decreases depending on how much voltage is applied to it. Thus, charge can easily flow through the diode in forward bias. Finally, we have what is called reverse bias. In reverse bias, either side of the junction is attracted to the charge that is applied to it, so the holes in the electrons move towards the outside of the diode. This causes the depletion region to widen until it occupies most or the entire diode. This gives it an extremely high resistance. Next, I will discuss IV curves, which describe the amount of current that an electrical device has when the voltage across it is adjusted. As shown, a diode has a relatively constant low resistance past the knee and nearly infinite resistance in the reverse direction until it reaches its breakdown voltage. The values for these threshold voltages typically depend on what material the diode is constructed out of. One common use for diodes is to rectify AC signals. Alternating current fluctuates as a sinusoidal curve, and a diode bridge can force the signal to all become positive. As shown in the second diagram, a smoothing capacitor can also be added to the circuit so that the resulting waveform is more like direct current. Another very common use for diodes is in LEDs, or light-emitting diodes. In LEDs, electrical energy is directly converted into light energy, which skips the heat conversion that is often necessary to generate light. This makes LED light bulbs up to 80% more efficient than traditional fluorescent bulbs. The color of an LED depends on its bandgap energy, which also depends on its material. For example, blue LEDs are traditionally made with aluminum gallium nitride. Zener diodes are another type of special diode that have the additional property that current is allowed to flow in the reverse direction intentionally. They're widely used as voltage references and as shunt regulators in order to regulate the voltage across small circuits. When connected in parallel with a variable voltage source such that it is reverse biased, Zener diodes conduct when the reverse breakdown voltage is reached. They also tend to have a highly doped p-n junction. Next, we will be going over charge-coupled devices, also known as CCDs. Charge-coupled devices are an important electrical component that captures light and processes its information, and it's commonly used in digital cameras, microscopes, and photocopiers. In order to discuss CCDs, I'll first discuss how camera sensors work. At a very small scale, camera sensors contain many photodiodes, which are similar to diodes as they often use p-n junctions, but with the difference that they only conduct in reverse bias. Their main purpose is to convert light energy into electrical energy. The photoelectric effect describes what happens when a material is struck by photons. In a photodiode, when photons with a specific wavelength hit silicon, it forms a pair of an electron and a hole. The electron naturally migrates towards the positive side, and the hole migrates towards the negative side. Thus, the presence of light can be measured by the voltage on top of the photodiode, and different voltages would represent different intensities of light. However, when scientists tried arranging a grid of photodiodes connected with wires in order to capture images, bits of charge are left behind, and a phenomenon called capacitive coupling occurs. This creates lots of noise and distortion in the image. As a result, CCDs were invented. CCDs do not require the use of wires, and rather only use a piece of silicon, which solves the problem of capacitive coupling. On the silicon slab, insulating channels and aluminum are placed in a grid. When the sensor is exposed to light, the charges build up along each of these strips of aluminum. Then, the charges are transferred row by row by shifting the polarity of the aluminum until they reach a readout register, where the image data is amplified and recorded by measuring the voltage of the charges. Another camera sensor that was invented in a similar time is called the CMOS, or the Complementary Metal Oxide Semiconductor. In contrast to the CCD, each pixel has its own capacitor and amplifier. The amplifier in each pixel prevents the issue of capacitive coupling, and the signals from the pixels are processed in parallel, allowing for faster speed. CMOS also has its own drawbacks, such as having more noise present and rolling shutter, which makes moving subjects and images appear distorted as it can only process one part of the image at a time. CCDs and CMOS sensors have been competing for many years. CCDs have passive photosites that capture information and move it to an amplifier. In contrast, CMOS has amplifiers at each local photosite. This means that CMOS sensors can have more variation due to having more amplifiers, which results in having more noise. CCDs also generally have higher quality pictures and have better light sensitivity and less noise. However, they're also costly, consume more power due to the current needed to move the charges, and are also slower due to the parallel processing in CMOS sensors. The advantage that CCDs had over CMOS sensors has decreased significantly over time. As a result, CCD imaging is mostly used in professional settings, and consumer-grade cameras typically use CMOS sensors. Photocells are essentially resistors that vary their resistance and are sometimes called photoresistors or light-dependent resistors. They're commonly found in light sensors to detect the amount of light present. For example, automatic lights, such as street lamps, utilize them to control when to turn on. However, they are also very inaccurate, and variations can be up to 50% among groups of the same photocell. Photocells also are different from photodiodes, as they do not have a p-n junction and do not directly convert light into electricity. Instead, they alter their conductivity depending on the presence of light. Photocells consist of a photoconductive material over a layer of an insulator, which is usually ceramic. The back and forth pattern of the material, which is typically cadmium sulfide, is created such that the desired resistance is achieved. Either side of the material acts as a separate electrode, which are then connected to wire terminals. Photocells also utilize the photoelectric effect, where electrons in a valence band are excited when struck by light. This causes them to move towards the conduction band. As more charges congregate in the conduction band, they allow current to pass through, thus decreasing the resistance of a photocell. As a result, the amount of light present is always inversely related to the resistance, which is shown in this graph. Based on its operating principles, it's pretty clear that there are a lot of uses for photocells. Some common ones are either as switches or as sensors. The circuit on the left is a schematic for a simple night light. In this case, the R8 resistor is the photoresistor. The operational amplifier, which is the big triangle thing, acts as a comparator in this case. This allows the photoresistor to control whether or not the lamp turns on. Next, we'll discuss solar cells. Also known as photovoltaic cells, They operate on the basis of converting light energy into electrical energy through the photovoltaic effect. It bears much resemblance to the p-n junction photodiode, but with some differences. The P region is typically much larger than the N-type region, and small electrodes are placed on the N-type layer so that there's minimal interference with the area that photons can reach. Similar to that of a photodiode, however, photons strike the junction and create electron-hole pairs. After the electron migrates towards the N-type region and the hole migrates towards the P-type region, a potential difference is created, and this allows the cell to act as a small battery and generate a voltage. There's also an emerging branch of solar cells called the dye-sensitized solar cell, or the DSSC. I'm only including this because I did my magnet research project on them in my freshman year. DSSCs are inspired by photosynthesis in plants, and they capture light energy using a photoactive dye. This excites the electrons, which are in a conjugated bond with the dye, and are stationed on titanium dioxide nanoparticles. A chemical electrolyte, such as iodide, ensures that electrons are returned to the dye, completing the circuit. Despite having lower efficiency levels than silicon cells, DSSCs are drastically cheaper to manufacture. The following animation shows the path of an electron through a DSSC. The white balls are the titanium dioxide nanoparticles, the small dots are the dye, and M is the electron carrier, or the iodide. Finally, the last topic I will cover is the transistor. The transistor, at its base, is a semiconductor device that can amplify or switch electronic signals. Transistors have two primary uses, as switches and as amplifiers. When a sufficient current is applied to the base of a transistor, it can act as a switch and be switched on. This allows combinations of transistors to be used as logic gates, which I will elaborate on later. Transistors can also be used as amplifiers, which can be used to increase the strength of a weak signal. Transistors can be classified depending on its use purpose. The two major classes of transistors are the bipolar junction transistor, or the BJT, and the field effect transistor, or the FET. In short, bipolar junction transistors use a small current at one of its terminals in order to control a much larger current flowing between two other terminals. A field effect resistor uses an electric field from its gate in order to control current flow, allowing it to act as a switch. First, I'll go over the most common type of transistor, the MOSFET, which make up over 99.9% of all transistors manufactured. The MOSFET was invented in 1959, which was a revolutionary invention because it allowed for mass production of transistors. It is also the most manufactured device in history, and about 10 to the 22 of them have been created since its date of invention. Similar to diodes, MOSFET transistors also utilize doping, which is usually performed on silicon. Instead of a simple p-n junction, transistors contain multiple sections, such as an NPN or a PNP junction. The diagram shows the layout of a typical MOSFET. Two regions, the source and the drain, are doped with an N-type dopant, which each form their own depletion region along a border with a p-type body. This way, when no current is applied to the gate, the depletion regions prevent current flow across the transistor. However, when there is current to the gate, the electric field that is created between the gate and the body attracts electrons to the gate, which creates a new depletion region called the N channel that connects the source and the drain. This allows current to flow. The following is an animation that demonstrates this. As shown, in its normal state, electrons cannot pass through. However, when there is a charge applied to the gate, it creates a channel with electrons, which allows current to pass through. When more voltage is applied, a greater electric field is induced, which can increase charge flow. Here are two examples of logic gates that can be created using transistors. The first is the AND gate, which returns 1 if and only if both of the inputs are 1. It contains two transistors that both act as switches depending on the input current. When both transistors receive a sufficient current, they allow current to flow to the output. The second is the OR gate, which will return 1 if at least one of the inputs is 1. When either of the transistors receive enough current, current is allowed to flow into the output. Using transistors as switches, every type of logic gate can be made. Other examples include the NAND gate, the NOR gate, the exclusive OR gate, and the exclusive NOR gate. The other major type of transistor is the BJT, or the Bipolar Junction Transistor. As shown, BJTs are typically NPN and sometimes PNP. The regions are denoted as the collector, the base, and the emitter, respectively. An important difference between BJTs and MOSFETs is that MOSFETs depend on the voltage at the oxide insulated gate electrode, while the operation of the BJT is dependent at its current at the base. As transistors allow for the creation of logic gates, it allows computers to utilize Boolean algebra, which is the foundation for all computation. Millions of these gates is what allows computers to function. Generally, a smaller transistor can switch on and off faster due to physical limitations, which is why the semiconductor industry is continuously trying to produce smaller and smaller transistors. This leads us to Moore's Law. Moore's Law is a theory that claims that the number of transistors on a circuit chip doubles every 2 years. It has been relatively accurate as depicted in the graph until recently, as their size, which is in the nanometer range, is beginning to create problems such as quantum tunneling. As the barrier distances are steadily decreasing in order to make transistors smaller, they aren't always thick enough to block current. Electrons can disperse across barriers at finite probabilities, which is what is known as quantum tunneling. This is a major obstacle for chip makers, as it creates a limit for how powerful modern chips can get. There needs to be a new replacement for the MOSFET in order to keep up with the speed of advancement in computational power. There's research currently being conducted on transistors such as the tunneling FET, or the TFET. They utilize quantum tunneling by switching between the probability that electrons on one side of the barrier will materialize on the other side. And that concludes the presentation. Thank you for listening, and hopefully most of it made sense.